March 19th, 2021. This is a box of calibrated scale bars from November 2020. They've been in a box since about December. So we're gonna cut it open here and see how much they have bent on their own while being in storage. These have been in the office, at the state office. You know, I flattened them out right before I calibrated them and did the calibration and then put them back in this box. So let's pull some out and take a look at them. I'm going to pull out the full November set here, and we'll put them on this very flat workbench and take a look. Okay, so there's a California set in here also that was calibrated at the same time, but I remember this November 1 set was the first one that I'd done. Okay, so out of the box, you see it's got a little bit of a twist to it. It's pretty flat, it's just got a little bit of a twist to it. So I can correct that just by torquing it just a little bit. Maybe a little bit more. Yeah, there we go. Okay, so that really wasn't bent all that much. This one again, it's got that twist to it, and so what I've noticed, this is consistent with what I've noticed, is that I can flatten them, but then they kind of want to do that twist again after they've sat for a while. So there they are. Yeah, so they're kind of twisted a little bit, but you know, it's not too bad. So that's what those longer ones look like. Let's get some of these shorter ones. There again, it's got that twist, and I recall that I had pretty much twisted these perfectly flat before I calibrated. Now this one also has a little bit of a camber to it, so we would need to bend that one down a little bit and twist it. So it's a little bit out of whack there. That's also got a little bit of camber and a little bit of twist. These are very pliable, much more so than the older style bars that we got. Yeah, so that's kind of twisted itself again as well. See if I hold one end down. Yeah. And I'm using this workbench because I know it's pretty darn flat. Okay, so it doesn't take much to get them back into balance. Okay, so that shows you what's needed to get them back into balance on the longer bars. These shorter ones don't really change too much. They weren't too bent to begin with. There's a little bit of a camber there, but not much. Okay, so that one's good. That one's perfectly flat. Maybe a bit there. Good. These really short ones have almost no movement at all. Those are pretty good. And then these little guys, they're so short, you wouldn't really notice any. Maybe got a little bit of a bend to it. Okay, that's Nevada 01. And I'm just going to bend those back into place. Now what I want to do is bring out the California 4 set. And again, these have been sitting in this box since about December. I had straightened all of them out before calibration. Now what I want to do with these is examine how much they've bent, and I'm not going to correct them. I'm going to take these guys out for another calibration, and I'm going to compare it to what we had before. There's a little bit of a twist there, not too bad. That one's actually really good. Okay, that one's got quite a bit of a twist to it. That's got a twist. So they're all kind of twisting. More so than getting a camber, they're starting to twist as they sit in that box for a while. And that just must be something with, you know, maybe the internal tension. That one's actually pretty good. But I recall pretty clearly that, you know, I had twisted out, and that's got a little bit of a camber to it. I had twisted these back out to be pretty flat before I calibrated them. So they've definitely twisted themselves just a little bit. It's got a little bit of a twist to it. So a majority of these have bent while they've sat in the box. So what I'm going to do is calibrate these, and I'm going to compare these distances now with the calibrated distances that are written right on the sticks. And I'm going to use my steel calibrated rulers to make sure that I've got the nice baseline. And then we'll see what that looks like afterwards. Okay, so after collecting all those photographs, I took them all into Metashape, processed them with the steel rulers to measure the distances between those targets on the scale bars. And I have then a comparison between what those distances were in November and what they are in March. But first, it's worth taking a quick look at set CA04. This was a set where I calibrated it and then immediately ran the same set of images through Metashape a second time, just in order to see how much error is introduced just from the software side of things through the bundle block adjustment and error reduction steps. And so this is a spreadsheet on the screen showing those differences. Note that all the distances are in meters. So for each distance, labeled as the distance between, for example, A1 and A2, or target 11 and target 11B, there's the first calibration distance followed by the second calibration distance, and then the delta squared, and the square root. We'll do the square root so that we can get to the root mean square error, and I'll scroll down to the bottom half of the spreadsheet. And so when we sum all that up, we have an average distance error between first calibration and second calibration of negative 3.2 microns. When we average the root mean, or the mean square error, we take the root mean square error, we have 11.6 microns. That's pretty small, and the take-home message here is that the processing, the error reduction steps, even though they're designed to reduce or try to completely eliminate error, they still allow a small amount of error to creep in. And in this case, it's about 12 microns. So even though this would probably be better if we could replicate this many times, but just based on this one carefully controlled experiment, and it seems logical that you're not able to get rid of all of the error, and in this case, we're getting it down, almost entirely eliminating it, but we're still ending up with about 12 microns error from process to process. So let's take that information and then let's look at this California 4 set. This is the one we took out of the box, and notice the warp, and then took them without retwisting and rewarping, flattening them out, just photographed them again, and wanted to see after 4 months how much does this warp and twist change the calibrated distance that I penned in on those scale bars last November. So calibrated it in November, that's in column B, and then I just processed these the other day again, that's shown in column C, and then we've got the delta squared, and the square root. And we scroll down to the bottom of that spreadsheet, and we have some repeated calibrations here that are pretty close. They're not as close as taking the exact same image set and running it through twice, but they're still pretty close. A mean error of 80 microns with a root mean square error across all those calibrated distances of 82 microns. Now here's where it comes in handy knowing that the Colorado 4 set had about a 12 micron error. So if we assume that that's always going to be there, then we can attribute 12 microns of error just to processing again. So if we subtract that inherent processing error out of the 82 micron root mean square error for California 04, we can conclude that 70 microns of error can be attributed to the warp and twist occurring during the 4 months of storage of this set from November to March. 70 microns error is about what we're looking at then. So let's put that in perspective. Remember that the calibrated steel rulers used for the calibration are certified accurate to 4 decimal places. These are National Institute of Science and Technology calibrated rulers. And so we have confidence that the rulers are accurate to plus or minus 100 microns. Because of that, we're able to say that our scale bars are also accurate to 4 decimal places. I've always been skeptical that I see some of these scale bars to 5 and 6 decimal places. I've never found any standard ruler that professes to have an accuracy to that degree. So I don't know how you can calibrate something to be more accurate than the ruler that you're using to calibrate it with. So I stick to the 4 decimal places. Okay, so a change of 70 microns due to the warping and twisting, in this case, could result in an actual distance between 2 targets differing from the posted calibrated distance through rounding. I've got a picture of some of these bars. You notice I wrote it in here, so the one in the middle there is 0.2504 meters. The one to the left of it is 0.2502 meters. So let's take that one for example. And if we were to have an error of 70 microns, if we add 70 microns to 0.2502 meters, it comes out to 0.25027 meters, which rounds up to 0.2503, which is different than what's posted on the scale bar. The evidence doesn't indicate that this error would ever result in more than a 100 micron error, because this is just a rounding error at this point. But this is only a 4-month storage, so if these were to be stored for a few years, for example, and they get even more warped and more twisted, then you might see error that might extend to the many hundreds of microns, and you might be off, quite a bit more. So it's a concern. It's probably something that needs to be kept in mind for these scale bars, and periodically they need to be put out on a flat surface, I think, and checked for flatness, probably once every field season. It doesn't take more than 2 or 3 minutes to flatten them out. It's very easy, of course. Somebody's just got to remember to do it. Otherwise, you will probably start seeing a tiny bit of error creep in. Okay, well, that wraps it up.